Hello, everyone. So welcome back to the second session on Tuesday of IBC Astrostatistics and Machine Learning. So we will have a continued lecture by Dr. Utane Sawangwit on classification. As usual, please raise your hand if you want to ask questions, and I will ask you to switch on your video so you can ask your question directly. And remember that we will have the group pictures later at the end of this session. Okay, thank you, and you can please start, Dr. Utane.
Okay, thank you. Screen one, okay. All right, okay. Okay, so kind of going over the basics and kind of introduction of classification in the last part, with some mentioning of quite a popular, sorry, I just arranging my screen here a little bit. Okay. Okay. Right now, okay, yeah. So there was some algorithm name that decision tree has been chosen as a way to demonstrate the ideas and how decision is made. So that is just a simple, and even with that, decision tree is still one of those algorithm which are kind of like a go-to algorithm where you start off and want to do this type of classification. People still using decision tree or go for random forest and things like that, but it's still, at the end of the day, it's still quite a popular one and quite effective one too. Okay, so now let's explore a little bit in terms of various algorithm here. I pick out three of the algorithm. Decision tree, we cover a little bit on that. K nearest neighbor, as in, is this something that perhaps related to what we did yesterday? We have, of course, with the K means. So as you would imagine, this is kind of like a similar fashion, right? But in this case, since you have the label, so you know, so you have a kind of idea of this data points belong to this group and that group. So in that case, you can start to kind of try to construct this nearest neighbor if it's the same class. If they're not, then that's not going to be included, and so on. So that kind of given here to kind of show you what happened instead of clustering. If you have a label, then you get on to do something like K nearest neighbor. Although, yeah, we'll come to that in a little bit actually. And then probably half of the time, or maybe slightly more than half, will be probably spending on the convolution neural network. Okay, so you heard of artificial neural network before. So artificial is just generic term again. So the one that people using quite a lot is convolution neural network. The reason being that is can be used for a lot for object recognition from image, photos, and things like that. And convolution neural network, as you will see, is a way to kind of since normally with the pictures, when the number of pixels is quite high, as now you have many of these high resolution camera, because that give you a bit better detail and so on. These tend to become slow very quickly. So one way to address that is to have this convolution, as in you convolute, you don't need the whole pictures to feed in. Otherwise, you would need a number of nodes in your neural network, similar number with your pixel, which is not possible, right? So usually people kind of like convoluted down the features, and usually it just the system just recognize edge and shadows and here and there, and you don't need the full things, right? So, but again, having some information or details that still could pretty be useful. So anyway, so I will go into that in a bit with convolutional neural network. Okay, so let's starting on the decision tree. I mentioned about this in a little bit already. So again, is a most widely used technique for classification. The accuracy can be quite competitive, actually, given that it's something very simple and also very efficient too. So this is like I said, a go-to one. So if you're starting off, you do something very complicated, but you skip decision tree. People would ask you, have you done something like a simple decision tree or random forest and things like that, right? So yeah, so there's some code implementation that you can try and download, you know, a good implementation one by the name of C 4.5, things like that. So yeah, you can try to get those code and see how it goes. So again, we can now let's see learning by example. Here we stick to this loan kind of data. If you're a bank, try to decide whether it's worth considering or worth giving someone a loan, maybe. Then when you come to kind of this instance, let's say you have 15 customers. Of course, in real life, you probably need more data than this. But in this case, you know, seeing the feature is not that many, and so let's use this as a practice or demo kind of information. So in this case, what we consider as the features, right? Which of course, whether that is related or not, is very important. So that's where this domain expertise come into this, right? So loan data, for example, here we list age, whether that person has a job or not, whether that person already own a house or not, how is his or her credit rating, right? So you would think maybe just the credit rating is good enough, but for someone who never borrowed any money before, for example, that person credit rating could be very good, right? Because he never actually ventured into borrowing. But once he borrowed, who knows what happened, right? So credit rating may be one key important factor, but not everything. So you need things like age, and that's why you need things like also own house or not, because most often people who own house might, you know, have mortgage on it and things like that. So you can track a record on it. And let's say if someone were to come along and say, how about gender? You don't see gender here, right? So there's no gender as being a feature. So which you probably expect or not. I mean, depend on different person. Is it safer to lend the money or loan to a female than a male? Things like that, right? So so these are not there. So it's depend. Maybe someone somewhere put this in and feel like, okay, it doesn't make any difference, and then so decide not to include it. So as you can see here, is this just example and just show you why these features or attributes are picked, chosen in the first place, right? So as you can see, these are labeled data. So class here is a yes and no. So it's a binary system where these maybe from the past record, whether they decide to give a loan or not, and things like that, right? So if you were to kind of like construct the decision tree based on purely here, so as you can see here, the decision tree here based on age, right? It's pick age as the root node. Okay, so age here is a root node. As you can see, what happened here, the age doesn't run as a continuous value, but you know, age is a number, so you can have people ranging from whatever. If let's say over 18, then be allowed to borrow, then 18 to whatever, right? 80. But in this case, they want to kind of cap those, and then so this is an example of transforming or transforming your data, right, into the range where you can have only 3 groups here. So you have old, middle, and young. Okay, so whether young, what's the definition of young? You have to kind of get into detail of that. Older than certain age, but not younger than sorry, older than certain age, but not older than certain age and things like that, or younger than certain age, and then so on and so forth, right? And then, as it turned out, in this case, you start off by having age as a root node, right? So once you go down the age, which is a root node, you then check the attribute or feature. In this case, it's the age. Okay, so as there are 3 possible outcomes, so these are like branch that you can go down, right? Okay, so these are the branch that you go down based on the decision. Okay, so when we say decision, it's really rather a kind of logic kind of step, if, right? So if it's young, middle, or old, then you go through this path. And then once you go down this, you come down to the second level node, if you like. Okay, so as it turned out, if the person is young, the second important features that decide these classifications or decision is whether that person has a job or not. As you can see, this doesn't enter into different group of the age group. Okay, so it turned out that this quite an important feature, right, for young people, whether that person has a job or not. Yes, false. So you can see it pretty much depend on the answer. If that person has a job, then most of the time 2 of 2, right? That person will give in a loan, and if it's false, then it's a no. So it's a pretty good kind of a way to kind of classify people into exactly this category, right? And then if you go down different branch, in this case middle age, okay, the next features or the next node, next second level node you come to, this is whether that person own a house or not, right? And then it's kind of a similar situation here. So you can see here again, yes, 3 of 3, no, 2 of 2, right? And then once you go to the older category, it turned out that older category, perhaps most of them tend to own house, so that doesn't, and has a job, so maybe that doesn't kind of make a decising factor anymore, right? So that could explain why this is picking credit rating for the old group, right? So instead of, let's say, young, why doesn't young go to has a job and then has the next level node as in own a house, right? You don't see that, because you can see that once you hit the has a job, it's pretty much, you know, the answer is already kind of there. So there's no kind of like next node to help to decide anything. It's the same thing with the middle age. Okay, so that's why you don't see own a house and then go into has a job or credit rating. Now with the old age group, of course, these data are all make up data, right? They are demo. So in reality, it could be quite different. So anyone in the banking industry, don't quote me on this. So it's not meant to be like a reality of what's going on. Okay, so the next group, like, yeah, credit rating, you have a fair, you have a good, and you have excellent. So anything good and excellent, you get basically 100%, right? And if just fair, anything falls short of good, then no, it's 1 of 1. So this is a kind of simple case. It's black and white. You can see almost pretty much straight away. But if you were to go back here and see in the old age group, right, the person has excellent credit rating, own a house, but he doesn't have a job, right? So, but that is not a deciding factor. And another example would be this: old age have a good. Sorry, I hit the wrong screen. For example, the 14 here, the number 13, ID 13, have a good credit rating, has a house, doesn't own a house. Okay, false, but still yes. So mostly it seems that deciding factor would be on this credit rating, and this is why the age is kind of like a root node. As you can see, once you split people into young, middle, and old, it seems that each of them doesn't need to go down, you know, way further than just the next second level, right? Only just a second level and it's done. For example, if you were to start off with a root node like has a job, okay, you might find that once you have a job, you check the age and then you have to check some other thing, right? So that's why the way this is being optimization and implemented, this is the answer, because it's the way that build up a tree, decision tree, is the shortest, the quickest, simplest, right? So it's kind of like Occam razor, if you like, or the simplest answer. If it's suffice, why go to a more complicated one? Okay, so and then you can keep, you know, more examples, so on and so forth with different age group. Okay, so this is meant to be demonstration, which is very quick. So now, for example, if you have this decision tree as the model that you construct, so now let's say we have an instance, new instance come in, applying for a loan, okay, age, let's say classified in the young age group, he doesn't have a job, okay. For those who remember the tree, probably know what could happen to him, right? So that's quick. So it's just go down one branch and two branches, that's it, you get the answer. Nothing complicated. He doesn't own a house. He has a good credit rating, right? You see, that's the very different deciding factor, right? People in the old age group, if they have good credit rating, don't care about anything else, that person will get it, right? So this is really a deciding factor that with the young age group, if he doesn't have a job or she doesn't have a job, then the answer is certainly true, that is a false. There will be no loan given. Okay, so the question is then, would this kind of decision tree unique? Answer is, of course, a simple no. There's no, in this case, sorry, when we talk about this case, I'm not talking about generic case. In some other case, yeah, then there may be a case where situation is more complicated, right? This is a demo problem and it's very simple. So in this case, no, there is no other simpler tree, right? For example, so in this case, the demonstration here is if we want a smaller tree and also accurate, of course, right? At the end of the day, if you have a smaller tree, but what call is the accuracy? So how about this, right? Let's say if the root node, instead of being the edge, is being owning the house, true or false, right? The case that true, you got 6 out of 6. And false, you get, then you go to the next node. In this case, has a job, whether it's true or false, and it's pretty accurate, up to 100%. So with this, you skip through the edge altogether, right? So one could argue that this is probably, simpler tree, right? And in the case here, is probably edge. It's not even important. You can rule out the edge. Okay, this is very contrary to what I said earlier, right? With the age, you can pretty much decide, once you split the young, middle, and old, then yeah, each one would have their own distinctive metrics to decide. But in this case, seem like, yeah, own or not owning a house seem to be almost the deciding factor here. And then if that person doesn't own a house, whether he has a job, then that's again, you need to have those, because then you would see that some people own a house but still doesn't own a house but still get a loan, but only if he has a job, he or she has a job, right? So yeah, so this in terms of the decision tree we showed earlier. So that is, in fact, I lead you to the wrong conclusion, right? Seeing this as simplicity, so anyone would very quick to jump on that, right? But in this case, so as you can see, you have only 2 nodes, right? Level. So this is for level 1, level 2. But if you see the branch, it's much simpler. You have 1 branch, 2 branch, 3 branch, and 4 branch. Or you can see this as a sub branch, right? And 2 branch here, and that's it. Whereas here, right, the whole thing is much more complicated in order to decide. And if you have owning the house, that's very quick, right? True straight away, okay, without having to go to the second level node. Okay, so yeah, so this is a very important kind of like key message, that how finally your decision tree is made. So that's a kind of example. So you probably can see that in this simple case, it can be in fact, decision tree can be converted to a set of rules, right? In this case, it's not that hard, only a few features, so it's almost pretty much straight away can turn into, like we mentioned earlier, like the if statement, right? If, else, right? And set this up, yeah, you can pretty much decide straight away without actually any machine learning in this case. Okay, so in terms of the algorithm for decision tree learning, usually this is what the basic algorithm, that kind of like basic principle we use is what we call a greedy algorithm, sometimes called a subclass of greedy divide and conquer algorithm. With the greedy algorithm, usually what it means is it tends to go and explore every single combination. So what you see earlier is perhaps can be products of computer go and try all sort of different combinations. In this case, it could work out well because you don't have that many features to begin with. The sample is perhaps not big, and somehow it's been set in a way that is quite accurate to predict with those features. So with this, it's suitable for things like a greedy algorithm, right? Because it can explore all the possibility and determine the best solution. Okay, but most often greedy might not be suitable if you have a very big feature set, very big data set, and so on. Okay, so in this case, right, the attribute can be put into a category. Okay, in this case, it's kind of distinct, but put into like a discrete value. Although it can handle continuous attribute as well, you can see, right? With the age, you can subdivide into groups, so it does work. The tree that constructed, as you saw earlier, that's kind of a top-down, right? A top-down tree in a kind of a recursive manner. So that's a greedy algorithm. It's kind of try this, and then kind of, for example, you were starting from age, and then take the next, let's say young. You probably try all those other attribute already and decide, okay, this one is very accurate and the most simplest, and then is just settle on that. So yeah, so at the start, of course, there was the algorithm would start off from trying different route, right? In this case, with the three three parameters, four including age, attribute is quite easy to do. And then whereas attributes and selection and everything, you could select things like impurity, what I said earlier about the fraction, so that is the accuracy. In this case, we tend to see that it's almost like 100 out of 100%, right? In some cases, there will be some class where you can consider it's a impurity. So instead of, let's say, it's all look good, like owning a house, there's a case where maybe only 5 out of 6 that get the loan. Somehow one guy who got owned the house true somehow didn't get it. So even true and they get a no, right? So it's also possible that sometimes called like impurity. So in this case, in fact, you should have once it's true, you come to yes and no. No, in this case, it happened to be 0, all 0. So that's why this was not displayed here, and so on. And in this case, for false, you can go through this way and stuff like that. So yeah, so in that sense, you can try to kind of like select it on some of the trees, select on this impurity function. Of course, you try to minimize the impurity function, the one that doesn't fit in with the class that's supposed to be. So yeah, so that would be things that what we call the information gain from the learning process. And then condition for stopping the partitions is when all the instance or examples for a given node, right, have belong to the same class. Okay, so one node usually, yeah, you will have 2 outcome, right? So so for all the example from given node, you have assigned a class basically, right? So that's stop. So there's nothing that cannot decide further, or you cannot land it back to where it's supposed to be. So yeah, so or there's no remaining attribute to further partitioning, right? So you end up with basically a leave class the end of the line. Basically, you cannot, you cannot partition any further, or there's no example left. That's the condition where it will stop. Okay, so again, I kind of mentioned this in passing already. The handling of the continuous attribute, which is not how do you do that when you don't have like the value of something being yes or no, high or low. Then yeah, so you can try to split the two into something that continues into less than or higher than, or that sort of things, and that gives you a way to handle the continuous contribution. Okay, and sometimes that might not be obvious, right? like we saw earlier, in actual fact, there's no such thing as a young, middle, and old. There's an actual number. So that was like intentionally done to kind of like simplify example for you. But in fact, how do you define young, middle, and old, right? So if you have the boundary set in a way that could complicate things, right? Let's say if the boundary was shift a little bit between young and middle, right? So those conditions, like for example, if they are young and they have a job, then you get decided straight away. But if you're middle age, you have to check whether that person own a house or not, right? So if the boundary is somewhat shift, and it so happened that there is a kind of someone from the middle age group jump into the young age group, that doesn't have a job but own a house, right? Would get, so that would kind of like, yeah, make things a bit more complicated. So yeah, you could see that these are also depend on how you divide those boundaries. Most of the time, yeah, it's also quite a wise decision in order to sort some value, right? If you have things like continuous attribute in the increasing order and deciding on the threshold between the two adjacent values like we saw earlier, like young and old and things like that, and testing out actually the possible threshold, as you can see here, right, in order to maximize the gain, right? The gain in this case is the information gain. So if there's no information gain, in the sense that once you speak, like I said earlier, you have the threshold is somehow higher, and then you have middle age which didn't get the loan based on although he has a job but he has a house and things like that. So these will be kind of, you get stuck because you feel like there's an impurity there and you're not gaining anything. So yeah, so that will be kind of rule out, and so this combination will be in a way that to maximize the gain and to basically to simplify the tree as well. Okay, so example in the case, in certain case that you have a continuous space. In this case, for example, let's say feature x, you divide it between 2 and then less than or equal to 2. You see the distribution of point, right, with the black square and the empty circle there. So this could be a way to kind of split them. As you can see, it's very clean, right? With some caveat here. You can see this one here, this kind of class or this node, for example, this node, you can see there's this one between 2.6 and higher 2.6. So it's basically it's this box here. Okay, this box had been subdivided from this one prior to this one. So this one is in fact could be seen as overfitting, like we saw earlier, right? So it's good, it's perfect, right? Get everything right. Okay, so this is the opposite end of what we tried to make example of earlier. All right, in this case, this could turn into an overfitting situation, right? Whereas perhaps this node is not necessary at all. Okay, and you have to live with maybe in this case here things that less than or equal to 2.5. There's this one which you know, consider an impurity there a little bit. Okay, so here, as you can see with this threshold going down this side, you can get a kind of decision tree to work even for the continuous values of the attribute. Okay, and again, like I said earlier, in terms of overfitting with the tree can again overfit. You can see over there the symptom that you can think of in terms of decision tree is that you get the tree to go too deep or too many branch. Okay, this again would be similar to when we discuss cluster, for example. We start to have way too many clusters, right? And those clusters start to kind of focus on this tiny, weeny local points or distribution. So that can be a bad thing, right? Because it could be just only focus on those training data, and when it comes to testing data or the real big sample set of data could be bad. In the tree, decision tree case, you can do things like pruning. Okay, so pruning is a very kind of a tree related word, right? In order to kind of like cut certain node, in this case, pruning the tree. Yeah, so in this case, yeah, so you stop kind of what we call the pre-pruning, is to stop the branch construction earlier, right? So to decide and not to make it at all, or you have what they call the post-pruning. So allow it to go fully, right? And then come to consider that certain branch is not necessary, and then decide to chop from that node on and so on, or something like that, right? So this is yeah, so it's a way that you can do that. So this is an example from similar to what we saw earlier, right? So there's this tiny box here which has been made up to kind of like accommodate only this circle point that happen to be sandwiched between these two populations. These could be outliers or some noisy thing that could be potentially just spill over from these. So but so that's why we say this is probably overfitting, because it just tries to accommodate all the point in the training set, which somehow wouldn't be representative in the real actual data. So by pruning, for example, in this case, this branch, okay, is analogy or kind of removing this box here actually. So you have to tolerate having this circle here in this class. So you have to contend a bit with impurity there, but avoid overfitting, right? Because in the real data or test data, you could have more of this black square in this area, for example, and you would classify them as being the circle, for example. So that would be overfitting. Okay. Other issues with the decision tree learning is that sometimes things like form tree, you can try to construct a rule out of it, right? And then you can have a pruning, like similar to what we saw earlier. So decision tree, based on how complicated the tree is, how complicated, how many nodes and things like that, it could potentially implement it into something that could gain some inside information, right, into how things kind of different variable play or correlate or somehow tie into one another. What would be the main factor or deciding factor, things like that, like what we try to discuss with the loan example, right? So that things that's why tree could be quite interesting to give some people insight, given if given that the tree is not too too complicated. Another issues on this is how would you kind of like handling missing data, okay, missing values, okay, and also things like skew distribution, sometimes something. So this is a bit like, yeah, it's skewing. It's not quite bad as outlier, but sometimes you do have a skew distribution. Imagine like, if you have this Gaussian, sometimes you have this tail which could be positively skewed or negatively skewed. How would this be handled? Because when you skew a lot, you could imagine that this boundary of the tree of the criteria could be accommodated up to like 2 or 3 sigma, right? So providing they are not all too close together, the different sample. But if you have things that could skew the distribution, it means that even you have a well-separated region, you could have, yeah, like that circle thing, right? It might not be, it's not even outlier because it's still not that far from the main distribution. It could be a skewing due to skew distribution. Okay, so that could be a bit hard to kind of like handle these things. But the way to handle it, unfortunately, is to overfit, and that could be bad. Okay, so things like handling various attributes and classes with a different cost. So for example, in a case where you want to give more weight, okay, to different class or different nodes, okay, so this is what it means by cost if the weighting are not the same, right? Another issue would be things like attribute construction, things like, yeah, how would you choose the attribute, which is again a kind of a common issue there. Okay, so those are kind of decision tree. I choose this as a simple example, and I think you will hopefully have a chance to try it. And yeah, it can be quite a good performer. Surprisingly, when you try to go do something very complicated, SVM, various other things, and then you might just come back and see, but the decision tree, yeah, as simple as maybe, give you quite good answer. Yeah. Okay, next, let's move on to the k nearest neighbor classification, or the KNN. Have to straight right off here, KNN actually does not build a model, right, from the training data. So in fact, it's not. It's a learning process in a way, but it doesn't try to build a model, but rather kind of define the area a bit like similar to clustering, right? But in this case, since you have the label, okay, so you can specify that this is in fact the same class, and so they are considered neighbor. So if the object of different class, if they are close by, then they are not, but they will be taken into account. So there's some penalization that, yeah, is this one coming in here? So in the form like impurity, like we saw with the other algorithm, basically. Okay, so in order to classify a test instance, let's say D, so you have a data, right? Instance, test instance, or whatever. We avoid the word training here, right? D. And if you define a K neighborhood, again, K here would be similar to what we see in the K means. So you have to define how many neighborhoods, right? Or the K cluster. Before this, we talk about cluster. In this case, we talk about neighborhood. How many of these neighborhoods you expect? Okay, because this could be based on since you know the classification expectation that you have, you could have K defined as the label number of classes, or if you expect or if you suspect there could be some subclass within your class, you can define K to be higher. More often, you can define K to be the same number with the number of classes first and see how it goes with purity, right? If you test things like purity or performance and you feel like, oh, okay, purity is somewhat like not very good in terms of you don't see a clear distinction between different neighborhood, or the number that you split is not very good, then sometimes it pays to kind of like try with the higher number of K neighborhood, and you could potentially discover a new subclass, basically, right? Because subclass, as definition go, yeah, they do share some common trait in the same class, but more often the thing that make them into different subclass could give you a different answer, right? So yeah, so those will maybe show up as somewhat higher purity, even though you think you've done everything. So yeah, sometimes it pays just to kind of like try with the higher number of K in this case. This is all again applied with the clustering as well. Okay, so so let's say if you have a training instance or training data set with number of n, right? In the data set that belong to class CJ, then you kind of estimate the probability, right, of that class CJ given the data. Okay, so you have the data, you estimate the probability. In this case, the probability is being defined as n over k. So k being the number of classes and n is the number of the training set. Okay, so with that probability, then you can try to kind of use that of like a cost function or some sort to kind of optimize it. Okay, in this case, like we said from the beginning, no training is needed. Classification time is pretty good, tend to be linear to the yeah, you keep saying no training, but we refer to it like training set size. So you need something to start off, and yes, for the test case and stuff like that. So yeah, so usually it depends on the size of your instance that you're trying to construct this K and N region, for example. Okay, so algorithm normally would go something like this. D would be the whole total. Sorry, D, small d would be the total of your instance sample, and oh, sorry, sorry, swap a little bit here. So D is actually not distance, sorry, is the distance between let's say subgroup D, right? Subgroup D or class D to every other example in the D group, okay? And then you kind of choose the K example in those D group, all the data group basically, that are nearest to the D, that data, okay? And you can denote the set here with the P again, with the probability that we saw earlier. Assign the D, the data, of the individual data, okay, to that class, that is the most frequent. Basically is what the proportion, the p, that have highest number of time it happening, right? So basically this is sometimes called the majority class. So whichever class that tend to have a similar pattern of objects appear in that class, you assign to that class, basically. Okay, so K is again here the number of groups or class. It's usually chosen empirically. So you go and kind of changing numbers and see what happened, right? With a similar thing like what we saw earlier with the validation set, cross-validation set, testing set, right? And just try with the range of K and use things like, yeah, the metrics that we saw earlier and things like impurity, distance function. So this is again similar to the clustering we saw yesterday. It's crucial, okay? Whether you define it to be Euclidean distance or Manhattan distance. Okay, so again, this again depend on kind of like application that you want, right? You would think like things like sometimes you want a shorter distance, sometimes you want whatever the effect that dictate you would be the highest, the longest distance. For example, you look something at like supply route, let's say, to, I don't know, to North Pole or to South Pole, for example. Most often, let's say you have a outposts or stations, you might not consider the average distance between these like clusters that they have to kind of like self-supporting. Sometimes you want to consider the longest distance between the cluster, for example. So that's kind of example of what you would consider using a different kind of distance function and things like that, right? It's not Euclidean, it has to be Manhattan because there's no direct route to it. You have to go this way in order to avoid crossing the mountain or avoid crossing a giant lake and things like that, right? So that kind of thing. Okay, so to give you some example, let's say you have some kind of data set here where, I don't know, maybe some kind of organization or some worker, let's say, in the field of identified as being the government or working in science or working in arts, right? And these parameter space could be anything, right? Let's say it could be age versus education, like we saw earlier. It could be income or the price of the house that person earned and things like that, right? That's just example. Could be anything. So in this case, let's say this is the case, and then when we have a new point here, the question is, what's the where does this point, right, associated with? So let's say if you can think of it like what we say, like the probability that these objects are assigned to science, for example. So you have, in this case, you have 3 labels, right? You have government, science, and arts, but we go for something like K of 6. So it means that you start splitting this sample with the nearest neighbor into 6 groups, right? So once you place this point down, you will see that this point is closer to which group or which those subgroup of 6 is belong to. So let's say if that's the case, that's the area where it's confined to out of the 6, then it becomes a probability that this point could be somehow related to size, right? So given that square point, in this case, if this is such happen to be the region, right, you can see that the probability here basically just determined by the number of instances that turn out to be size versus, you know, everything in this case, right? In this case, you have 1, 2, 3, 4, 5, 6 instance. You have one such instance being size, so this is 1 out of 6. So if this object landed in this neighborhood, right? So this there are 6 neighborhoods landed in this neighborhood. The probability that this will be size would be 1 out of 6, right? Which is some 10% something. But if you shift the question around, what's the chance of this happen to be someone related to government sector, for example? Then it becomes 5 out of 6. So yeah, the order probability here would be improved. So this is a kind of example of what we call the kind of the K nearest neighbor. So in essence, it's kind of almost like what we saw earlier with the clustering, but in this case, you have the label. So basically, it's so you can call exactly, right, the region or the local neighborhood in this case, how many of those turn out to be that class and how many of these turn out to be the other class. So then you can get the handle on probability for objects that happen to land there, right? But both of them using a distance function, okay? Same thing. So this is an example. It's just a 2D parameters, could go into higher dimensionality and so on, right? So with the KNN, you can deal with some complex and arbitrary decision boundary. So, and give you a nice probability, a likelihood if you happen to be in that parameter space. If there are more of one class, okay, it's more likely for you to be that class, and less likely to be the other. If it so happen that in that neighborhood you happen to have some other class join, some impurity, you can consider, for example, in this example, you can consider this side as being impurity if you like, because without this point, you could have this whole neighborhood safely say it's 100% government sector, for example. Okay, so yeah, KNN can deal with the complex and arbitrary decision boundary. Again, despite its simplicity, it has been used quite a lot and can have quite a good accuracy. But as you would imagine, the area where this can be working well is the area where you have a dense data, right? If you happen to land on the area where it's sparse, so with that you don't have a lot of things to kind of help you with, right? This area, it could be grouped together with, I don't know, with the red or with the black, but happen to be land middle where there's not a lot of data. Sure, you can, you know, get some handle if it's included with the red area. It could be like 100% size, but it doesn't mean that it cannot be art, right? These are, you know, the area where the data is sparse, and that can kind of like make your probability estimation kind of not accurate. Yeah. Okay. But either way, this is something that quite simple that people can use quite a lot, and give you quite a good handle on the classification based on position in parameter space and so on. Downside is perhaps the KNN is slow at the classification time. This is probably have something to do with the process where you have to count every kind of single thing in those area, and you have to kind of like split up and modeling and things like that. But when you come to classification time, then yeah, you have to kind of like counting. Sorry, I keep saying that, but actually training is not the point here. It's the classification time, because you don't do the training. So in fact, there's no boundary, there's no pre-drawn region, right? So there's the region you see here as neighborhood is happen, you know, run like a how shall we say, a kind of like a write-off, a dynamic real time. When you want the answer, there's no model, pre-model, because there's no learning happening in the background. You ask, okay, if k equals to 6, what will happen? So then it's have to find this region straight away and start counting, right? So that, yeah, that with the big data set, it can be slow with the classification time, because you have to count the objects, whereas things like when with the model, you're mapping already the region, or you have like some empirical function that you can plug in the value, and straight away you get the classification out and things like that. Okay, and unfortunately, this KNN doesn't produce, unlike the things like decision tree and things like that, where you try to gain some understandable or physical underlying physical model. KNN doesn't offer that, but it's offer you a way to kind of like classify how likely it is for an object or instance to belong to a certain class. Okay, now we have another 45 minutes. Okay, that's good. Let's talk a little bit about the neural network. Okay, particularly on the convolution neural network. That seems to be one of the quite popular one, especially when you have to handle things like image. But by the way, it doesn't only apply or exclusive to things like 2D image or anything like that. You can apply to 1D data as well. things like light curve. People try to do that, or sometimes go to use something like recurrent neural network, INN. But you can see CNN is being applied to things like light curve as well, 1D data set. Okay, so it's probably quite interesting just to have a look at this and see what it all mean. Okay, so just to go into that, let's start off by seeing what is actually neural networks. Okay, and then go into what actually going on with the convolutional neural network and how it's different from the normal neural network. Okay, and then there will be some application or quite interesting or famous or popular like convolution neural network application, things like that, right? So we can go into that. So yeah, so okay, start. So as I mentioned earlier, the artificial neural network is designed to kind of try to mimic how human brain, or maybe animal as well, so it's not just human, make decision on certain things, right? It's turned out that it's just a series of synapses and neural network, basically one after the other. So you can imagine this network as being a node, like you saw earlier, right? With the decision tree, you have different nodes, and then you can send to the next layers, right? The technical term for neural network we call layers. You have a different layers. The more layers it is, it's become more complex, right? Like a bit like what you saw with decision tree. You can have root and then second layers, and if things simple enough, like loan example, you finish in like 2 layers or 2 kind of node level. But in this case, again, so if you have, it probably goes that if you have more nodes and more layers, it's good in a sense that it will work better in order to give you a good accuracy, but that comes at a cost. You need more data. Like again, we said there's no free lunch. More node means you have more free parameters that you have to work on. More degree of freedom, you need more data set, more training time, and so on. And again, it could go into things like overfitting. So again, so now come back to this part. So yeah, so this in this case is kind of try to model like a brain. It's kind of like you go through one synaptic node, but if the nodes or layers are too little, it will be too simple, right? It would be just like you put in some input and ask, okay, does this satisfy this condition, and then just go straight to output. As you can imagine, in the complex system, right? It could, you know, it doesn't just ask one node and that's it, and you get the result, right? So then you have more layers to accommodate those complexity, basically. So you can go, for example, if this is the case, it's channeled to this node on these layers and things like that, right? We'll see in a bit. Okay, so draw some analogy with biology. If this is kind of like a nervous system, nervous cell, right? You have this cell, you have this dendrite tree. If you think of it in this sense, you can think of this as a part where it's kind of receive all the signals or input, right? That come through the dendrite tree. Okay, so this is what we call neuron, and usually from this cell you go through various these biological structures that maybe mostly tend to be like wrapped around by things like fat and things like lipid and things like that. So it kind of have certain threshold like to trigger. All these are all electrical signal, right? For example, you poke something in your hand, you feel pain. That's electrical signal, right? Sent from your skin to the cell nearby there into, let's say, if it's let's say if you poke hard enough, right, it will go to kind of trigger, right, or what we call the to activate the cell. So all this stuff here in the middle acting like a thresholding or kind of activation to kind of to say, okay, is this important enough? Is it worth actually telling the brain that someone poke me, or is it just place a hand on the table? There's nothing really important here to talk about, things like that, right? So if it's turn out that the system determines this is important enough or pass through certain threshold or activated, then it will go toward the final, or it could go through various layers, right? It could go and then finally out to the output. Okay, and then things like the cell here could act like what we call the integration, because you have various different input, right? As the cell on the skin, you experience various different input all the time. It could be heat, it could be pressure, it could be light, depend, right? If your cell, depend on which cell, right? If your eyeball, then you probably sensitive to light and things like that. So yeah, so that is kind of like you have different input feed in, and then kind of integrate it and kind of like make sense, and then somehow send the signal to this, and then this part will kind of like thresholding, decide whether it's important enough to relay the message. If not, then forget about it, right? Things like that, or to relay to which part and things like that, for example. Okay, so in the sense of like computer science, mathematical algorithm, this is what the neuron would look like. That integrator is this one, right? So you have all different input feeding into it. In this case, let's say it's the M features or M attribute, right? Of certain data, right? You feed in the input that have M distribute. This is where it different from the normal biological neuron. They have this what's so-called bias. So you add another term, as you will see that there is this kind of linear combination between different parameters here plus weight. So the weight is basically tell you for certain data set or for certain phenomenon, this parameter is more important. Okay, the other one is not so important, so the weight could be less and things like that. But this bias is kind of like something that is a constant offset that add in all the time. You see that it's just adding for mathematical convenience to help with the how we model these. And then all this, you know, kind of like integrator, right? Integration is a summation, right? That's why the sign here is summation. Put it all together through some kind of activation function. So that what resides in the activation function is actually each different node will have the activation function on it, right? And then you can have various different nodes. You can have many layers, right? Sometimes called hidden layers. And then on that particular layers, you have a node. The node on the same layer wouldn't connect to each other, but rather connect to the next layer. Okay, we'll see that in a bit. And then finally turn out the output. In this case, it could be classification, right? Like analogy would be if a human sees something from the eyeball, the signal sent, and then you kind of, okay, with all this activation, it goes through various neuron in your head, that this feature that you think, oh, there's this animal. What is this animal? There's a long ear, there's a fluffy, there is a short fluffy tail, happen to be chewing carrot, right? So it goes through that different layers and start to kind of deciding and finally come up with the best output or best answer. Oh, it must be rabbit, for example, right? But if you were to look at something that a bit in the darker room or in the zoo, and you cannot make out all the visual that well, or maybe not even eating carrot and things like that, right? Then you could probably think it is, but it could be a dog or anything else, right? So yeah, so just to say that these are also depend on your information as well. If your information come in thick and full and good quality data, then yeah, you have, so basically your brain cell, your neuron are all kind of like trained system there already, and form your experience because you grow up. So all those years you learn by reading books, by your teacher told you, your parents, your TV watching, whatever. Yeah. So okay, so now let's look at this. So for example, at each node, so you can see that this is summarized. So this is what happened at each node of the neuron. Okay, you can have the input that coming in with various attribute. Okay, like we said earlier, attribute or features, right? X1 to whatever xn. The feature that you feed, it could be, I think you will see in example during the hands-on on the Thursday, we'll be using neural network for things like photometric redshift calculation. So basically using things like photometry from different band, or basically it's color information, right? And could be other things, not limited to that. Could be also luminosity and things like that as well. So this, you could imagine that this X1 and to Xn is whatever, could be a photometry in U band, G band, R band, I band, whatever, and various other band or other parameters as well, size or whatever that feed into it. Okay, and the whole training thing is to actually work out what are these weights, okay, with this W, okay, at this kind of different node, as you will see when, so these are, we still kind of using one node, one neuron, okay, so it's simple, right? For that different node, for that exact parameter, you have this set of W, right? So it's almost sound enough like a linear kind of problem, right? You can solve it as long as you have, let's say like n unknown plus bias. If you have enough data, right? Like n set of data, you should be able to solve it. So yeah, so that what it is. Okay, so once you take into information here, integrator is where you sum it all up here, and then depends on what your activation function, right? So activation function here, using either O here or in the picture here, use a G. Okay, so by using those combination, or rather the input into activation function, then it's determined whether, let's say, once the signal is sent to this neuron, whether this is important enough, or this neuron would, how would it react, or how would it send to what node and things like that, right? And then it turns to output, let's just say. So yeah, so this is quite a key concept in terms of the activation function, and that's what, in fact, is what kind of behind what why we call the neural network that kind of mimic neuron. So yeah, the difference between biology and this kind of like software engineering or coding or computer science is this bias term we talk about. Activation function, of course, this is a mathematical implementation. In reality, of course, is using, we'll see, okay, so it could be something like a threshold function, right? Things, if the value reach certain threshold, then it will be either 0 or 1. It could be a step function, right? If nothing, if it's not enough signal, it will not jump to trip off like a switch at all. So it's like binary. Or sometimes you can have something, a more kind of continuous function. So even if the function is not like full on to 1, you can still kind of gradually, so you still have, you know, some partial activation if you like. Okay, so that's different. Okay, so the area of activation function, or the choice of activation function, can be quite important too. People can spend quite, you know, quite some time in order to kind of like check the performance of their neural networks classifier, choosing various different activation function. The one I talked earlier, that's what we call the threshold function. Okay, like this one. So it's like a step function where you know, if you don't have enough sum up to get to 1 in certain, then it's just 0. Okay, so you have to get on that level, otherwise basically just 0 or 1. Okay, so nothing in between. Another one which is quite popular, you hear a lot of this, is the sigmoid function. Okay, which is basically is 1 over 1 plus exponential of minus x, x being the input. Okay, so the input earlier, if you remember, is w0, the bias term, plus w1, x1, blah blah blah, all the way to wn xn. Okay, so then that is what the activation would be. So that would be determined by this function, or sometimes it can be this max choice, right, between 0 or whatever the parameter that you feed it, which is x, right? So if something is 0, then it stays as 0. If it's non-zero, then yeah, it will be that value. So it's a bit like y equal to x, that kind of thing. And this is sometimes called the ReLU function. Okay. Yeah. Again, this function would be differentiable, right? If you compare this to the threshold function is not continuous. It's jump up, and so if you try to differentiate it, it wouldn't hold because it's not continuous. But whereas sigmoid and ReLU would give you those differentiable, that could be important because, again, like we talked earlier, things like gradient and things like that, when you try to optimize the learning process to go down the path where gradient decrease the fastest, right, in terms of like cost function and so on. In this case, the cost function could be the difference between the features, the output that you predict. I think I have some slide at the back. I should wait for that. Okay. Okay. In terms of bias term, you might ask, so what is this bias term? So to kind of represent the example of the activation function here, using the sigmoid function for different various input, right? So various different x there. So you can see that for if you don't have the bias term, what happens is that they all tend to be kind of very close to one another in the sense that it's quite hard to distinguish, right? That the signal come in from, let's say, X input in this, let's say, for one instant or one object or one galaxy. Let's come back to this photometric redshift analogy. Have this parameter in the magnitude, right? Some with some weight, yeah, the value could be a bit different, like you see here, 0.5x, 1x, 2x, but to the node that decide would be, they still look somewhat very similar, right? But whereas when you put in this kind of term into it, the bias term W0 for different node, then you can have a more kind of distinguishing power, okay, to it. In this case, then even in this case, you can see that here the input to the normal X, which is not the bias term here, all the same, but even that you still can distinguish them. So that's why the bias term is there. But again, it's become another free parameters or degree of freedom where it has to be fitted, right, for different parameters. Okay, so neural network is nothing new. Okay, it's early as 1950s, and you probably know that machine learning idea itself is not new either. There's people proposing this for some time ago. It's only up until recently that this gained popularity again. As you could imagine, the computing power required for this is quite high. The data set for training is also quite high. So in the past, neither of these are available, and so it were pretty much just theoretical curiosity or academic curiosity that we think, okay, if we such and such, right, like you would see in mathematical theory, basically. So yeah, so now neural network is pretty much from a huge family of machine learning model, especially with the classification, you name it, there's so many, right, that followed by an N. I mentioned earlier that you have a recurrent network where things kind of like back propagate and feed it, things like that. But what we're going to see with this is the feed forward network. Okay, so this is so let's say you start off, so in the term of this neural network, you tend to consider things in layers. Okay, you have input layers, output layer. Okay, so you can start off with input layer, let's say parameters that you feed in 10 parameter. Okay, and then finally at the end you get only one single output out, right? It could be photometric redshift, you feed in photometry, you feed in size, whatever colors, and then you get out what is photometric redshift. It's the system thing it has. Or it could be classification, right? Classification could be put into class 0, 1, 2, 3, 4, 5, whatever, right? So you end up with one number. So all these going on here is to decide what path it will go to, and then what output value of the output will come out. Okay, so as you can see, so these, sorry, I pointed the wrong scheme again. So here, these would be considered these nodes. Okay, these are different nodes that reside on the same layers. Okay, and then once the information all you can see that this is a one-to-many connection, right? So all the input will feed to all the node. Okay, and then this is of course quite different from decision tree, right? Decision tree, you start from something like a root node, that's it, right? Here you have many nodes, okay, in the same layers, and the same layers are fed the input all at the same time. Okay, all the informations, and as you can see, the node on the same layer are not connected to each other, but they are connected to all other nodes in the next layers and so on. So if you imagine, you count all the combination, right? If you were starting off from here, go to here, and then come here, let's say if this path has high activation value, for example, right? It will go through this path, and let's say when the next layer come to this path and things like that, right? And then finally arrive at certain output value, right? It can be different if it were to go through here and go through here. So if you imagine by adding more nodes and more layers, how that give you quite a complex network to kind of tackle complex problem, right? So yeah, so once you so this is again is pretty much how you would try, and again there's nothing set in stone that how many layers and things like that. So but there's sometimes a rule of thumb, things like how many layers you should go to, or things like a decision tree. how many level of branch and things like that that you should go through. These are mostly when you implemented it, which are mostly sometimes in the order of number of the features you feed in. Could be one time or twice, but in the order, okay? It's not in the order of like twice the number or something like that. So usually, yeah, there's some rule of thumb, but it's not, you know, set in stone. You have to test out and try what works for you, what works best for you, and things like that. Okay, so this is how things are kind of wired together in this neural network pictures. And as you can see, things are all feed forward. Okay, so there's no coming back, and you can see all the arrow here, all feeding forward. Okay, there's no feeding back to update what we call the weight function. Okay, so when it goes through here, what it does change is that x is always the same, right? Input is always the same, but you can scale is what you can scale is the weight. Okay, the weight W1, W2, whatever for that particular node. So when you change that, when you kind of like get those W, as you would imagine, you would have to start off from something like a first case, right? Like a first initial value, and then you kind of pass to the next layer and so on, and then finally arrive at the answer. But since these are supervised machine learning, you have a label, so you can check the label with the real data, right? And then that gives you like a cost function. So to minimize those cost functions or minimize the mistake, then you can train the whole thing again. What we call is epoch. So you can training into different epoch, okay? But at each epoch, they all always move forward. This is different from things like recurrent neural network. You can backpropagate and then use the weight from the last one, inform the previous one, and so on and so forth. But in this case, we stick to this feed forward only, okay? No recurrence. And it's all fully connected, so, okay, between layer, no connection between neuron in the same layer, as I said before. The cost function is this, okay? The data DJ, let's say, which is the ground truth, okay, the label, actual label of your data, whereas yi is the output, okay, after passing through those layers of neuron. So basically, what cost function is, you know, its cost is high if you keep getting it wrong. So usually, then you try to minimize the cost function, and you can retrain it again and again with different epochs and things like that, okay, until you improve it. But most often, in the first few epochs or first few, I don't know, 10 or 100, you can see the cost function going down, or sometimes we call loss function, going very well. So cost function can decrease very quickly, but up to a certain point, even though your accuracy is not that great yet, but you find yourself where you cannot, you know, improve this further, then you have to kind of try different things, right? Like whereas different parameters, the way you scale it, or whatever layers, or yeah, all those things. Okay, so with training, okay, so all that is basically what we call the stochastic gradient descent. Okay, so it's pretty much kind of stochastic means just basically kind of random and some kind of like back propagation way to kind of like arrive at the final answer. In this case, what to do is to get the minimum cost function. So what you do is you differentiate those cost function based on W. As you can see, it's a partial differentiation because there are many W. So it will happen at, you know, different nodes. This will be happening. So yeah. So and finally, you come up with the base weight. Okay. So basically, finally, what the model you get is basically this structure of the network, and then you have this weight, okay, of different parameters W1, right, from the input layer to hidden layer 1 and so on. And then for the same node, for example, then you have W2 from whatever, okay? So, and all these nodes could have all those weights are different. So you can imagine how many of those free parameters the whole thing need to learn and kind of solve to get this into the optimal answer. Okay, so yeah, so the backpropagation here is in terms of updating the weight from the last layer to the first layer. So this is when you do the epoch training, when you go back, okay? So you do backpropagate in that sense. It doesn't do the recurrent like we said earlier. So yeah, when you start the new epoch, this weight go back to kind of like, yeah, feed to the first layer in order to kind of optimize it, not from the beginning, but rather learning. So that's, you know, term learning. Right, so again, with this neural network, so let's see what this convolution neural network actually means. Okay, so let's say if you were to have layers that looking like this, let's say for simplicity here, you have 2 hidden layers, okay, and then you have 1 input layers that could be pictures image, right? In this case, could be like 512 by 512 pixel, right? So it's not that big. And you have extra information like the RGB, what color it is, and things like that. So as you can imagine, this will be like a data cube, right? So you have a value of red, what value it is, green and blue, and so that turns into the color that you see, and the amplitude that add up could represent intensity, okay? But if you don't have colors and you just have intensity, then it's just 1D multiplied by 512 by 512. So as you can see, the layers have to kind of act on something kind of similar. Although the output layer, finally, you kind of like, yeah, you could scale down to the outputs of your class that you like. Okay, in this case, yeah, we say it's a 3-dimensional, 512 in height in terms of pixel by 512 width, and with the depth of 3 for the RGB. But if, let's say, you train image, which is from normally the scientific camera, and it's monochromatic, so it's just 1 color. But if you bring, let's say, you want to do that, map the pixel together, and you use, let's say, U band, G band, R band, or whatever else, right? So you can potentially see how you would do that with a different filter band with your data. Okay, so information is in fact in the form of pixel, right? Pretty much in line with what you normally do, right? So if you were to multiply all the independent data here, you can see that there's about 780,000 inputs, okay, for this 512 by 512. And so in the first layer alone, right, you need to calculate all this weight, right, per neuron, okay, this per neuron. So yeah, so that's very important too, right? How many neurons you have. So now how are you going to map all these, right? You have basically 780,000, right, for W. So that is something crazy, because you want to have more neuron for the model to be complex, you have more layers, but hey, this is probably not possible. So what you can do in this case is to do some kind of data reduction, okay, one of which is also a requirement here in terms of locally connected region here, which basically you can, yes.
Reminder for 15 minutes.
Okay, so you can subdivide your data here into, let's say, 5 by 5, right? Like a sub box. In this case, you would have a kind of like what we call convolution, but your convolution is basically a kernel, okay, like a top hat kernel in 2D, right? Because it's X and Y. And then you take everything in RGB, but yeah, but those kernel have the width of 5 by 5 in this case. So instead of feeding individual pixel to the node, now you have kind of reduced down into like 5 by 5 by 3. So then how would you map that out? Of course, you can do things like striding and things like that. So in this case, let's say if you were to do like window size of 5 by 5 by 3, now it's reduced to something like 75, right, weight per neuron. Okay, so per dose, for example, if that is the sample size you get. So and in that case, here, so depend on how you would put all these neuron. Okay, so let's say if we were to have this depth of neuron, okay, the hidden layers, that's the same hidden layers, and let's say if you were to use 5 neuron, okay, per that layers in this case, right? So this is what it's going to look like if you multiply by the data with the height and everything to consider all the possibility. So with this, right, with the input, let's say of 10 by 10, this is just to get an idea of what happened once you kind of like sample your data. If you start off, let's say by 10 by 10, you do a window of 5 and you kind of like doing striding of 1 pixel at a time, both to the left and then to the bottom as well, things like that. So you would get something like a 6 by 6 output, right? So each time you would get this grouping of 5 by 5, and if you do this for 10 by 10, you end up with finally you get only 6 by 6 output, okay? That group together. So fine, good. We get this kind of like working formula, n minus W, and being the elements of the window that we want to consider. W would be the window size that we try. Divided by stride, we could make the sample smaller by making a stride bigger, right? Can have an overlap striding like you saw earlier, just go 1 or you go 5, right? So that even reduce the number even further. So this is what kind of like what happened here. So let's say if you do the whole thing for 512 by 512, you end up with something like 508, right? Input. But okay, how about if we try to go bigger step, stride of 2, right? The problem with that is, okay, you cannot, because 10 minus 5 divided by 2 is not a full number. So you cannot have the output size not a full integer. So that's not possible, but there's some way around that. You can padding 0 to the border, like similar to something like this. You can pad a 0, right? So now it's good because you can get the kind of integer, full integer output into like 10 by 10, right? And that kind of like, yeah, so kind of help. But again, have to be careful with this padding, okay? Otherwise can lead to something like washing out, because basically things like around the edge here, you see that you kind of put in this 0 padding for, you know, more than half, right, of the elements. So have to be careful with the edge effect. Okay, so let's say if you're doing this stride 1 and with some padding and things like that, so you can basically reduce down this number. Okay, so before this is if you have 5 neurons, right? So the number will be something like this, right? From the parameters that you feed into. So you would end up with something like 98 million weights. Okay, this is total already, right? Per, not just per neuron. Before this, you have 700,000 per neuron. Okay, and if you multiply up, yeah, so that's huge. So for example, this is why we do in such a way, whereas you can keep all the data. Okay, and this is like subsection of the image. Okay, I will keep going somewhat a bit faster all the way. Okay, so now once you do that, you will start to introduce what we call the convolution layers. Okay, so instead of going from input and then to the hidden layer straight away, you introduce this something in the middle called convolution layers, which is, you know, basic like we saw earlier, things like with features, right? It's just a transformation of features basically. In this case, we use this convolution layers, and then sometimes you can reduce the number of parameters you have to optimize further by using what we call the pool layers. Okay, so pool layers then can come after the convolution layers. After that, after everything's finished, then you can do the fully connected layer. So that's just before the output. So the pool layers would work something like this. Okay, things like used to be your subgroup together here, like the convolution layers. So this would be something like that, probably come out from your convolution layers. So now when you're pooling, okay, so you reduce from, let's say here 4 by 4 to just 2 by 2 by using depends on what you want, right? People can use max pooling. Basically, this for pixel, which the value that has the maximum value will assume the new value here for this pixel, or can be median or average and so on and so forth, or minimum even. So that's again depend on the application. So when you do that, you get the max the pooling. Then you can use that to kind of like feeding into the next level, like a fully connected. So that's normal layers that you normally have. You can have different striding kind of like strategy, right? You can have when the window size is exactly equal to striding, so that's no overlap between them. Okay, it's called traditional pooling. Or you can keep some overlapping because maybe you're concerned that you might lose some information by you know, jumping over and then just like reduce down from, I don't know, 5 by 5 to just 1 pixel. Okay, so then that's yeah, good for that. And sometimes, yeah, you might think use a larger window size will help, but in certain cases people will try not to do that, because depending on the feature size that you expect in your image, if your feature size is quite small and you use a large window size, it means that those features could be, you know, washed out, take average or taking max with other features next to them, so you could lose the information. So that's not very good. So, and then you end up with the final fully connected layers again. So that is the traditional neural network that we saw earlier. that finally give you an output, right? And now it feeds the pool layers as the input. Okay, so even that, there's still these many weights in the CNN that you still need to do, right? With the big image size and all that, right? Our example only do it with 512 by 512. In fact, you can have 1K by 1K camera or 4K by 4K. Okay, so the training is really time consuming, and again, the caution about avoid overfitting by putting in way too many hidden layers and stuff like that. So here you can see that if we were to do convolution in steps, right? This is example starting from something like an image 32 by 32 and reduce down to 16 by 16 kind of like thing at convolution that reduced to 16 by 16, not reduced by 16, because otherwise that would be too big, right? So you reduce in step, and you have this convolution layers that reduces down at first, and then you pass it through this pooling, or you can go to ReLU first. Okay, in this example, you go through some kind of activation function first, and then have this convolution again, and then activation function again, and then pooling. So you reduce the kind of the data dimension, and then as you can see here, then it could then be further reduced by convolution and so on and so forth, and finally to final fully connected, where you feed in all those neurons that you get the final answer as classification. In this case, from the picture, is it truck, car, airplane, ship, or horse, right? So
okay.
Yes.
5-minute reminder.
Yep. Okay. So these are some. I think I'm probably not going to go into detail, but just rather just mention in passing. As you would imagine, this is very big applications, and there are many people publishing or putting out code of their algorithm. Okay, these are a few of the very popular one. Some ResNet, RENet, some of them has even higher version and stuff like that, have various way of implementing it. You could, of course, make your own and write paper about it, or put it on GitHub. And if it's doing great, you can perform on various benchmark tasks, things like handwriting alphabet, right? There's this various test data set that always available online where you can do it. Another one which is also very popular is this AlexNet. Okay, I don't think I put ResNet here. You can look up and see what strong point and weak point compared to one another, and you can see there that architecture of different CNN network here are quite different. Here you have a different striding scheme, you have different pooling scheme, and so on. Okay, and even more. So applications, all these that you normally see in the people tend to talk about, right? Things like classification from image, objects, whether it's what type of vehicle it is, what type of animal, what type of plant, flowers, and things like that. So yeah, and so that seems to be what you see a lot of that, and there are no shortage of like Python notebook if you want to try those, right? Another thing is to detect changing human pose as well. So if you can imagine this have to track real time, right? What that person is doing, because sometimes information just as a still image is not good enough. But if you have a streaming movement, then you have this extra information to guess what people are about to do, right? In terms of security, things like that, terrorists. People can anticipate this guy look agitated, or there's something that he keep reaching into his pocket, weapon, etc., etc. And then yeah, the security or whatever can take a decision. Another application is this making high resolution image from low resolution. So let's say you're stuck with some low resolution image, you want to reconstruct, right? So there's a way where you can. So this is almost like seem like the opposite, right, from the CNN, but yeah, it could be reversed. And use this to kind of get the high definition resolution image out of the low one. So things like toolkit, there's a lot of tools, right? Things like Cafe, CNN. I'm not sure scikit-learn have one probably. And then things like if you want to use GPU CUDA to extract those, Cafe has it, TensorFlow has it, and things like that. So it depends on those network or algorithm that you want to use, you probably want to check these are themselves like a platform or things like that. Most of them tend to have interface with Python and things like that, or R, and you have to check for your platform of choice and things like that. Okay, so just to conclude with the final slide here. So with the CNN based on locally connected and parameter sharing, we saw already, they can keep quite a good performance, especially when you have all these multi-dimensional imaging that features and stuff like that can be quite, even with the convolution that you reduce down the resolution, you still can get a very good classification of that, all of these features. So two things here that, of course, can be an issue here. Things like time consuming, as you can imagine, all those neurons that you have, hidden layers and all the parameters. So that's why I think like CNN kind of like try to help these things to go faster, and things like overfitting. And more often than not, sometimes we use the pre-trained model instead of a training of a new structure. So in fact, you might not start off from a completely blank slate. You could get a network from things like AlexNet, and like what I said earlier, sometimes they have pre-model that train with various, let's say, depend what you're trying to do, right? You try to classify objects, human, animal. Sometimes there's this already, and you can kind of use that further, build on to your particular set of data, things like that. Okay, so that's it for me. Thank you very much.
Thank you very much.